Hello, everybody. Good morning. Yesterday was hot, huh? It was really hot. And last time I was working with the radon detector in such hot weather was a couple of years ago in the Seychelles, and the radon detector decided it was too hot and shut off. And it was, there was so much heat and humidity, it got into the system and couldn't handle it. So it was good that we were not on a boat yesterday in that heat and have the same problem. That was special. I'm living in North Germany. 36 degrees doesn't happen. It was pretty exciting. Anyways, today we're going to move on with our topic. It's a continuation of yesterday's discussion. But today we're going to focus specifically on the radioisotopes, radium and radon, to quantify submarine groundwater discharge into coastal zones. Because there's some work behind this that I think is important to understand. So most of the day, most of the morning, we're going to be talking about work we do on boats, which honestly is a lot of sitting around and applying sunscreen. Because these detectors do a lot of the work for you. That being said, you have to make sure you're checking them all the time to make sure that the data that you're getting in is correct. So we're going to talk mostly today about sampling and quantifying groundwater discharge via radium to start, because that was kind of the first big breakthrough. And then we're going to move on to radon. And then I'd like to introduce a new idea at the end of this, where we can use a GIS to get a very quick and easy understanding of where submarine groundwater discharge might occur. And the reason I want to do this is A, it's interesting, but B, not everyone has access to radon detectors. Not everyone has access to radium delayed coincidence counters. But these days, everyone has access to GIS. And the availability of digital elevation models is improving worldwide. And obviously some places have very high resolution digital elevation models. I'm talking meter resolution or less. But global digital elevation models are essentially already available at 30-meter resolution, if not better. So this is something that anyone can do anywhere in the world. And as I've gotten more into science, I'm really trying to focus on doing things that people in, for example, small island developing nations can do without access to the scientific resources that we have in the United States or in Europe. And therefore, I think it's important to hear about this, no matter where you are. Okay, so we'll start with radium. Just a brief recap from yesterday. We all know that now the SGD is happening kind of all over the place, and we have a sense of why it's important. In many cases, that why it's important can also be a negative situation, bringing too many nutrients into the coastal zone, bringing too many pollutants into the coastal zone, too much carbon dioxide into the coastal zone. But there are also positive impacts of SGD. We talked yesterday a little bit about freshwater availability, if we can capture that freshwater available. That SGD itself may be preventing saltwater intrusion. One thing that I did not really talk about, except on the first slide, is that certain plants and animals preferably live in areas with SGD because it's bringing in either colder water, which the animals like, or potentially coral reefs too, in areas where the ocean is warming too much. It's also bringing in nutrients, which things like seagrasses may really have an affinity to in areas that are generally oligotrophic. So it's, there are positives to SGD. There are positives and there are negatives, but we know it's important. Yesterday we talked about different ways to measure it. I started with the point measurements and the bulk ground conductivity, and then moved briefly into the, let's say, high-tech measurements of radium and radon, and that's what we're going to now do today, is go further with those two measurements. We all know now that radium and radon are daughters of uranium and thorium. Uranium and thorium are generally found in rocks. So radium and radon are tracers of groundwater that's passing through rocks. They're elevated in groundwater compared to surface water. So when we're trying to sample for radium, as you remember, we go out in a boat and we go around our coastal area or our lagoon or our bay. Any place with salt water, you wouldn't use radium in a freshwater lake. As I mentioned, there's that salt interaction that needs some salinity to release. And you collect large volume samples of water. 25 liters, if you know that there's going to be radium in the water in a coastal zone with limestone where you know there's going to be groundwater coming out. 50 liters if you're in more of a, let's say, diffuse SGD environment, so a typical sandy, unconfined aquifer, then you want to get bigger samples, just to make sure you get enough radium to measure it, to have a quantifying thing. And if you're out in the open ocean, so when Billy Moore did his global survey of radium, he was collecting 1,000-liter samples. So he had enough to measure the actual radium. So you collect your sample, and then you slowly filter it, really gravity filter it through these columns. And these columns have manganese oxide fibers in them. And the manganese oxide fibers, it's really just cotton, you know, like the cotton balls that you actually impregnate with this manganese oxide fiber. And then you stuff it into these columns. The water passes through it slowly, less than 1 liter per minute. And if it passes through it, then the radium strips out of the water and goes onto the manganese oxide fibers. And what comes out at the other end is radium-free. And then you can dry them and count them. And so we count the short-lived isotopes, 223 and 224, by alpha detection using the delayed coincidence counter here. And that takes about an hour and a half to 2 hours to do each sample, and usually you can do 2 samples at a time in the system. And then you basically pulverize the rest of the fibers and turn them into pellets and measure the long-lived radium isotopes via gamma spectrometry, and you can get then your activity of radium in the water. And the idea is the higher radium you have, the more groundwater is coming out. That's generally the case. So yesterday we briefly talked about the mass balance. Today we're going to go really in depth into this mass balance. So in order to take those samples that you've collected in your lagoon or along your coast and turn that into an actual number of SGD, so an actual flux in liters per day, or centimeters per day, or cubic meters per day, however you want to describe your flux, you need to know your mass balance. Because the unknown in the mass balance is always going to be the SGD. So we do a mass balance. I drew it on a quick box on the board yesterday, and now we're going to talk about it today. So, assuming your radium in your area, your lagoon, your bay, your coastal zone is more or less in steady state, we can do a mass balance where the outputs must equal the inputs. So when it comes to radium, you essentially have two outputs. You have the decay of radium, the radioactive decay. Especially those short-lived isotopes, especially 224, which only has a 3.6 day half-life, we will lose in a typical lagoon, a typical bay, a lot of radium to decay. We will lose radium to decay. The second way we lose radium is just the movement of water outside of your area, of your box. So how does the water leave the box? That's the second important output. So these two outputs must equal the inputs. So the first input, that's kind of easy to understand, is that often this box is not a one-way system. Often it's a tidal situation. So we have radium that's leaving at the ebb tide and radium that's coming in the flood tide. So we have inputs into the box, and that's a really important part too. So this is this exchange in. That's what's coming in via the tide every single day. Then, in many cases, we have rivers that are leading into our box. So we have to measure what's coming in via rivers. The river discharge, it needs to be known, it needs to be measured, or at least you can have it essentially an average over time. And then you also have to measure your radium in your river. And you can get your river input. As you'll see in a few slides, we also did this work in a place called Jamaica Bay in Long Island. And in Jamaica Bay, we have massive sewage inputs through sewage treatment plants. And so we have to measure also the radium in the sewage, which is not in here in this one, but it would be another input. Then things get a little bit more exciting. Then we need to measure how much radium is coming off sediment, which is known as desorption. So when the sediments are resuspended via wave action, or brought in via rivers, how much radium comes off that sediment when it hits a salinity of 7 to 8 parts per thousand. So as I said, the radium needs that salinity to go into solution, into water, otherwise it stays on the sediment. And so basically you need to understand this sediment resuspension. It's a bit difficult, we'll talk about that. There's also diffusion of radium, meaning that there's molecular diffusion that occurs across that sediment sea interface where some radium, it's usually a very small amount, but some radium may just naturally come into the water column. We're going to talk about how we measure that in a minute. In many of our coastal areas, we have salt marshes. And those salt marshes are flooded at high tide and drain at low tide. That's not SGD, that's just the draining, the movement onto the marsh and off the marsh. But as it does, that water comes into contact with sediment. Salt water comes into contact with sediment, and so it may be then increasing its radium activity and bringing that into your open water area. So you need to also measure your marshes. And then your unknown will be your SGD. What's left over will be your SGD. Okay. So we've done this a lot. And we're going to talk about a few of these in the next 20 minutes or so. The first paper we published on this back in 2007 was really kind of like a co-authored work between myself and my good friend Aaron Beck, where we did this radium mass balance in Jamaica Bay. And this is our most cited work, so we're very happy about this. But it's really introduced this topic out there. And now we're going to go into these points, these different inputs. So in Jamaica Bay, and we use J for Jamaica, This is our mass balance. So J out, that's what goes out through the inlet, plus the decay. Those are our movement outside of our box. It must equal J in, what comes in through the inlet, J wastewater, what's coming in through the wastewater, the diffusion, that kind of simple molecular diffusion across sediments, the marsh inputs, the desorption from suspended sediments, and finally SGD. Finally SGD. Okay. And so I just mentioned what these are, so you know what they are. What you notice is not here are rivers. There's actually no river that goes into Jamaica Bay. It's only sewage. It's the only surface freshwater input, so we don't have rivers. But I wanted to go a little further with this, and I just took some notes to be sure. What each of these, how do we measure each of these things? Okay. So let's start with J out. So J out is simply V out, and I'll get into what V out is, times C bay times the tidal cycle. How many per day? So this is really like 1.9 per day. Oh, sorry. In Jamaica Bay. 1.9 per day in Jamaica Bay. V out is the tidal prism that leaves at each low tide. And this is going to be an average over a spring neap cycle. Because during spring tide, we have a lot more water going out than during neap tide. You know what I mean by that, right? Spring tide is when we have the full moon and the new moon and the tides are really high. Neap is the half moons. So V out is the tidal prism. And C bay is the average concentration of radium in the bay. So that's your J out. The tidal cycle is easy. Your C bay, you should be able to calculate now via the samples that you took. And the tidal prism, if you're lucky, somebody's already done this work for you. And if not, you have to take hydrodynamic measurements in the inlet, which are possible to do. But once again, that's why I like going to this GIS thing at the end, because then you don't have to do it. Okay. All right. So the second one, the second output is J to K. And J to K is simply the volume of the bay times the concentration of the bay, so the same here, times the decay constant of radium. That's your decay. Okay. Those are your two outputs. And for this, you need to know your average residence time. Of the bay. So how long the water stays in the bay. Okay. J in is essentially J out, except instead of the prism out, it's the prism in. And instead of the concentration of the bay, it's the concentration of the open ocean several kilometers offshore. So you have to, when you do these radium mass balances, you also have to go offshore and measure the concentration in the open ocean. Because unlike radon, which basically is gone once you go offshore because of the atmospheric evasion, it just leaves, it's never going to last that long. Radium stays, so you have to measure offshore as well. So that's the J in. J wastewater is essentially the volume of the wastewater times the concentration of the wastewater. Pretty easy. And then things get a little bit harder. And I'll show you how we do this. I'm going to erase these two. Those are our mouse. J diffusion equals the flux, the diffusive flux of radium, and I'll show you how we do that in a minute, times the area of sediment in the surface area of the sediment in the bay, in the box. That's J diffusion. J marsh is kind of the same thing. It's the flux from the marsh times the area of the marsh in the box. And the flux from the marsh I'll talk about in a second as well. And J desorption is what's known as SZ times V bay. So that's basically the amount of suspended sediment times the per liter times the volume of the bay in liters times the desorption flux of sediment. And what you're left with then, if you can do all of these things, what you're left with is SGD, which is simply the leftover radium after you've done this, divided by an end member concentration. And we're going to talk about that in a few minutes because the end member concentration is a bit complicated. So it's simple and complicated at the same time. Okay, so we'll talk about the end member concentration at the end. Okay, so how do we do diffusion? How do we get the diffusion input? The J out, the J in should be relatively clear how you do that. The J decay is just essentially the decay constant times the volume of times the concentration of the bay times the volume of the bay and the residence time. So those are relatively easy to calculate. The wastewater or the river water is also straightforward. You measure it directly there and then you measure how much is coming in. But diffusion, we have to do something special. We have to create a diffusion experiment. So what is our diffusion experiment? Our diffusion experiment is we basically get a couple kilograms of sediment from the bay in different locations in the bay, and then we put them in these buckets and we fill radium-free water on top. And then we measure the radium in the water essentially every few hours for a couple weeks. Maybe a little less than every few hours. In the beginning, more frequently, and then over time. And you try to figure out this curve, and that gives you your diffusion coefficient. How do we get radium-free water? No, we don't know for sure if that's radium-free. We don't know for sure.
Maybe if you leave it, just letting the radium decay for a while.
Maybe if you had enough time, but there's a lot. Remember, there's long-lived isotopes too that go into short-lived isotopes. You have to take distilled water and pump it through manganese oxide fibers. Because whatever radium might actually be in distilled water will be removed by the manganese oxide fibers. So this is our desorption experiment, and then, sorry, diffusion experiment. And this, it gives us our diffusion coefficient, or diffusive flux. We also have to do the marsh. So what that means is going out into the marsh and measuring a couple tidal cycles and seeing how the radium input changes as the tide goes up and down, and then being able to integrate that change over your tidal cycle and then multiply that by the area of the marsh. And the remaining important flux is this sediment resuspension radium desorption issue. And the way we do this is we do a desorption experiment. We take 5 grams of sediment and we put it in 20 liters of seawater and we shake it. We shake it. We basically resuspend the sediment. We do that for a little while, and then we cut the water out, and we can get how much radium desorbed from those 5 grams of sediment. And then the trick is estimating daily sediment resuspension, which in a simple bay system is relatively easy, but like on the coast here would be a disaster, trying to, in a wavy coast, to try to understand that. Which is once again why radium is not the best for coastal areas. Now radium loss by decay I already talked about. Okay. So that's how we calculate all of those things. And what you're going to learn, or what you're going to hear about or read about when you think about radium a lot is uncertainties. And each of these things have their own uncertainties. And those uncertainties propagate, right? So if you have uncertainty in one measurement, and then you multiply it by the uncertainty in the next measurement, and then multiply it by the uncertainty, and then all of a sudden your uncertainties get quite large. And this has been a problem for radium for a long time, but I think it's important to talk about. Okay, and then we also have to find the right end member. We have to find the right end member. So that's also a difficult question. What is the right end member? Is it a well somewhere on land? How far on land? Do you get the well water for radium? Radium is changing via its flow path because of the sediment interaction and also because of this subterranean estuary where the salt is already mixing below the ground. So for a long time they were measuring it really in these wells and then making your final quantification, because the final number is really dependent on the end member. If your end member activity is very high, then that means that your radium concentration will give you a very low SGD calculation. If your end member activity is low, then it will bring up your SGD calculation. So it's really dependent upon this end member. So we struggled with this for a while, and then we came up with the idea of trying to collect pore waters directly in the bay. So as close to the surface as possible after all these processes have occurred. And so we did this. We, in many places, we collected pore water. We used this system here. This is what's known as an AMS gas vapor probe, but we obviously like to work with water, so we used it for water. You basically pound this into the sediment, and it has a little nozzle on the top and sort of a screen that blocks a lot of sediment from coming in. And then when you get to the point you want to be, you pull up, and it opens this tip. And then this is connected to a tube, which is connected, originally we were doing this with a hand pump, but we need 20 liters of water. So trying to hand pump out 20 liters of water from clayey, silty sediments can be very difficult. We eventually got a peristaltic pump and would build little constructions from pieces of wood or whatever that we found in the area with a car battery and use that to pump it out. And we ended up getting our end member that way. And our end member measurements were not all exactly the same. And so what we did was we used an average of those end member measurements to do the final calculation. There's more uncertainty there. But we still believe that this is a better method than measuring in a well 20 kilometers inland and all of the things that can happen in the path between there and the sea, especially for radium, because radium, and once again, has the salt interaction. So you need to understand that. Okay. So once we have all of these things, we can get a final calculation. And we did this for Jamaica Bay. And when we did this for Jamaica Bay, our final calculated discharge was 40 to 52 cubic meters per second. Jamaica Bay is not a very large bay, just in Queens and Brooklyn, New York. And 40 to 52 cubic meters per second is a good amount of water, especially if you think about the watershed and you take the complete recharge possible from the watershed, that the amount of fresh water, unless somehow the groundwater level is really changing over time, the max you can get is 11 cubic meters per second. So this assumes that there is no water entering this bay, no fresh water entering this bay other than through groundwater. The max you can get is 11 cubic meters per second, and our radium calculated discharge was 4 to 5 times as much. 4 to 5 times as much. If you remember this from yesterday, radium also measures recirculated seawater, right? So this water that just goes through the sediments, not fresh groundwater that's coming from land. So the maximum amount of fresh groundwater is 11 cubic meters per second. Radium, 40 to 52 cubic meters per second. 5 times as much. A lot. So then we went to Venice and spent a long time in Venice doing these studies to try to answer the question, how much groundwater discharges into the Venice Lagoon? The Venice Lagoon is a fairly large lagoon. It's 550 square kilometers. The city of Venice is here in the middle. The famous city that everybody sees the photos of is just this little part right here. There are 3 outlets to the sea. There's a major industrial zone. They do pump, or they did pump groundwater into this industrial zone. They don't really anymore. There are, some rivers coming into the Venice Lagoon, but the major rivers were moved north and south of the lagoon over time. And just about 100 kilometers away from this lagoon are the Dolomite Mountains. So a major recharge area for the Venice Lagoon. So we want to figure out how much groundwater discharges into the Venice Lagoon. So we went out there and we did radium sampling one time. We did all 4 isotopes and we saw some patterns. We tended to have high radium for all 4 isotopes in the northern and high radium in the southern lagoons and lower radium in the central lagoon. We went back and we did our mass balances. And, once again, we have our J out, J to K, J in. We use J anyway, I don't know why. J marsh, J river, diffusion, and these are the numbers we got. So 4 times 10 to the 10th liters per day. Let's say 3 to 4 times 10 to the 10th liters per day of water coming in via groundwater discharge, depending on which isotope you use. What was nice is that they agree pretty well. The 4 isotopes agree pretty well. 4 times 10 to the 10th, so is that a lot? Well, all the rivers only bring you 3 times 10 to the 9th liters per day. So that's an order of magnitude more, 10 times as much via radium groundwater. There's 10 times as much groundwater coming into the Venice Lagoon via radium calculation as rivers are bringing in. If this is true, that's amazing and really, really, really important for the ecology of the Venice Lagoon. Extremely important. And I don't know if you know about this, but Venice has a lot of ecological issues. There's a lot of things that are happening in Venice via sewage, via heavy metal contamination on the edge of the industrial zone, and groundwater could be just pumping this right into the lagoon at 10 times the level of rivers. So that's kind of scary. So we went back and we did this a bit further and we tried to understand it more. We separated the Venice Lagoon into different systems based on hydrodynamic characteristics, working with engineers from the National Research Council of Italy. We started to look at, how much was the volume in the area, the depth, the residence time, marshes, river input for each of these basins to try to understand if there's something happening in a particular basin that's more important. And we did then tried to understand both short-lived isotopes, 223 and 224, in each of these basins for 6 different seasons. So this was a lot of work. I basically spent my life on a boat in the Venice Lagoon for 2 years, year and a half, riding around and collecting samples. I was stopped a few times by the Coast Guard, thinking they thought I was poisoning the lagoon. It was pretty intense. They had to call the mayor of Venice, who was the brother was one of the scientists, so it worked out. But with all of these, we started to get a sense of what was happening in the lagoon via radium. And here on the bottom this is the SGD compared to the total volume of the basin. So in many cases, we're looking at 10% of the total volume of water in the northern basin, and even up to 14% of the total volume of water in the southern basin is coming from groundwater based on these radium samples, which is a lot. It's a lot. Once again, there's something here that's not functioning right. We started to look at residence times in the different seasons that we did this work. So how long the water stays in the Venice Lagoon. And you can see the residence time is quite variable depending on the season. So for example, in the fall of 2007, the residence time is quite low. The blue colors, the cold colors mean that the water flushes out really quickly. Whereas in the winter and spring of 2007, the residence times were quite high. Does that have something to do with it? Well, we did find that in general, SGD seemed to be higher or calculated higher in times of low residence time than compared to times of high residence time, which we should talk about for the aquifers. It's quite interesting. So it does seem that residence time affects your SGD calculation. And it's a big difference, right? This is almost an order of magnitude difference between 5 and 65 times 10 to the 9th liters per day. So there's something wonky going on here that we have to understand better. Anyways, after all of this work, what we found out was that radium calculated discharge, once we removed a couple uncertainties based on the end members directly pulled from the lagoon, was 160 to 970 cubic meters per second of water coming into the Venice Lagoon via groundwater discharge. The entire input from rivers is 35 cubic meters per second. It's too much. It's too much. So radium starting to concern me. In fact, then we go back to our famous paper here by Billy Moore and colleagues. Once again, where they used radium, they say it's the SGD is 3 to 4 times greater than the total flux of rivers in the ocean. And I'm reading this and I'm thinking, with our data and what we're showing and things like this that are coming out, I'm starting to lose my faith that radium is a good way to quantify groundwater discharge. And this next study that I did in the Lesina Lagoon, Italy, scared me the most. Because here I have radium distribution in the Lesina Lagoon. And I think anybody, a 2-year-old, could read this and say, there's a lot of blue here, and there's not much blue here, right? So we have a lot of groundwater here, and we don't have much groundwater here. And then at the same time, we measured nutrients, and there's always supposed to be a lot of nutrients coming in through groundwater. And if you can see, there's also a lot of agricultural land here. And we measured nutrients, and the high nutrients were exactly the opposite of the radium trend. Exactly the opposite. Which made me wonder, is the radium really telling you about fresh groundwater discharge? Is it really telling you about fresh groundwater discharge? It turns out that there are a few just little streams here that are coming off a bit of agricultural land really close by. This farmer does use a lot of fertilizer, et cetera, but there's very low nitrate in the area with high groundwater. And so and it's funny to I spent years, a half a decade doing radium research. And I'll sit here and tell you that I don't believe it is the right way to measure groundwater discharge. And I will get very much, let's say, criticized by some of the people who work in the field. But they'll say, but it's measuring recirculating groundwater that's going through the sediments. That's also important. Okay, but it's not as important as fresh groundwater coming from the land. So if radium is not the answer, maybe radon is. Because radon is not affected by salinity. It's not being released because it's coming into contact with salty water. So I started playing with radon in a lot of different places. And one of the things is obviously you have to measure it on the boat and what we call radon mapping, but you also have to measure on land. This is actually really cool. This is in Dingle. What, do you remember when we did this? I don't know. It was probably 2 years ago, 3 years ago? 22, 3 years ago. And it was raining so much at that time that spontaneous wells or spontaneous springs were just popping up in the countryside. That's really a spring that just popped up because it was raining so much. And in Ireland, they talk a lot about holy wells. So I have wells that were blessed by saints or whatever. And I have a colleague who says that it was just the Irish way of explaining why water would just come out of the ground randomly at random times. A holy well, sign from God. Anyways, so we've measured this in many different places, and we're starting to really get the feel for radon. So once again, I talked a little bit about radon yesterday, but I'll bring it back in. How do we do it? We essentially want to collect surface waters, and we tend to pump it through either what we're going to show, I'll show you in a minute, a mini module or a rad aqua system at around 1 liter a minute. And then the RAD 7, which is that instrument I brought you yesterday, measures the radon via this sniff mode, where it pulls in the radon into the radon detector and measures the decay of 222 radon to 218 polonium via alpha particles. And so it measures those alpha particles, and then we get an activity. There were two ways to remove the gas from the water. The original way, which is by the company that builds the RAD-7, is via what's known as the Rad Aqua, which is this thing here, which is an air-water exchanger. Essentially, you pump water into the Rad Aqua. The Rad Aqua then sits here, and air is also getting pumped into the Rad Aqua, and that air is then causing a bubbling, which separates or allows the radon gas to release, and that radon gas goes into your radon detector system. So here we have as our Rad Aqua system. It's sitting in sort of a little box or enclosing, and that water then fills up and eventually goes out. The water comes in via the pump. Water from pump comes in, it gets sprayed down. We have then air being pulled out through one small desiccant, so something that's drying the air, because you don't want to have humidity in your radon detector, then through a large desiccant, which dries it even more, goes into your radon detector, it gets measured here, comes out of your radon detector, gets dried again, and gets sent back in to the system. The Rad Aqua, it was a disaster to use this thing, especially on a boat that is bouncing and moving, because if air gets in from the bottom, because this is not a closed space, if air gets in from the bottom, it screws up your whole detection. It's not really a good closed system. Maybe if you're sitting on a pier and measuring for 12 hours, it works, but on a boat, it was not good. But luckily, somebody came up with the mini module, which I call a lifesaver. And I mentioned this yesterday. So this is the mini module. I will pass it around the room. Essentially, water goes into the mini module and goes out of the mini module. But in this mini module, there are all these hollow fiber membranes which increase gas-water exchange. And then the gas goes out of the mini module and into the radon detector, and then out of the radon detector and back into this, and then leaves. It's a really nice system. You also only need one desiccant. You don't need two, because you don't have all of this spray and nastiness happening and getting more moisture in your air. So if you look at it, you can see how it works. Pass it around the room. And it really makes life better, this system. It really makes life better, this system. So, what I mentioned yesterday, which was really exciting with radon compared to radium, is you don't have to collect large volume samples and then filter them and then take them back to the lab and measure them. You can put your radon detector on your boat with you, and you can go around your coast. You can go around your coast, and you can measure and measure all the time, and this is known as radon mapping. So this is not my work, one of our colleagues, and here you see the radon activity is this kind of stringy line that's going through the coastal area in these different spaces, and the high radon activity is in red colors, and the low radon activity is in cold colors. And then these blobs of colors, that's the temperature data. That's the temperature data. And so basically you can see, you can just kind of ride around an area and measure radon as you go. You can map radon as you go, and you can get a sense of what is happening in your coastal zone. So one of the questions is, how do we know where we're measuring? And I think this came up yesterday, and I really looked into it. And these guys, Peterman and Schubert, actually from Germany, published a very unknown paper. Very few sightings of this one, but it's a very clear paper where they say there is essentially a 10-minute response time between your measurement and where the water came from. So you should really be looking back when you have one detector 10 minutes in time. I've always been under the assumption it was more about 5 minutes in time, but they did a bunch of experiments and showed this delay in time to be 10 minutes. So as you're going around your coastal area with your boat, as you're going around your coastal area with your boat and you're measuring, the point that records is actually recording kind of the 10 minutes behind you. 10 minutes behind you. So then you're always kind of 10 minutes in front. So if you see a peak in your radar, it's actually from where you were 10 minutes ago, not where you are right now. So there's about a 10-minute response time. And so you can really go around in your area and try to understand your radon values. Here you see radon activity in your blue boxes, your tide in your kind of blue dotted line, and you get a sense that yes, radon is a bit dependent on the tide, which is what we expect. It's also something we didn't see with radium. Radium tended to be a bit tidal independent when we got it, which is also another sign that it doesn't make sense. Whereas we know from yesterday, SGD should be higher at lower tides, and radon shows that. So it's a good sign that radon is working. So here's another kind of example of where you have thermal imaging, and this thermal imaging shows potential locations of colder, well these are boats, but potential locations of springs, and then you could go back there and measure your radon in those locations. And that's something I talked about yesterday, was if we can mix thermal imaging with radon, we can really get a good sense of where submarine groundwater discharge is occurring. So it's kind of just more evidence that radon tends to be a better way to measure SGD than radium. Once again, our highest radon values tend to be similar to our lowest tides. Wet season, dry season. So I did some work on this. This is the Dingle Harbour in Ireland. And in Dingle we have problems of eutrophication that occurs, specifically on this end of Dingle Harbour. And no one really knew why, because there's no fresh water from the surface coming into the Dingle Harbour. So we went around, we measured radon kind of everywhere in the Dingle Harbour. And at the same time, we took some DO measurements along the coastline, so dissolved oxygen measurements along the coastline. And here we see where we have low dissolved oxygen, we tend to have high radon. We tend to have high radon where we have low dissolved oxygen, which is what you would expect if the groundwater is bringing in a lot of nutrients. So unlike radium, where it was kind of the opposite of what we expected, with radon, it seems to really represent what we expect. So we can start to use radon as our better way of measuring submarine groundwater discharge. So once again, this is actually kind of a cool study right here at this Coast Guard station. There's a lot of groundwater. It's just, after it rains, you just see kind of like pumping out right from one little hole in the ground somewhere right about there, which matches our radon activity. And back here, once again, as I said, there's no surface streams coming in. There's a big surface stream that comes in here. But back here, there's no surface streams. It's all just groundwater that's coming out, which matches our very low dissolved oxygen measurements comparatively to the open water. Okay, so with our radon activity or with our radon detector, we can also do a mass balance. We can do a mass balance. And the nice thing is with radon, the mass balance is actually a bit more straightforward than it is with radium, because we're less concerned about some of that salt interaction than we are with radium. So once again, we have this mix. So this is in versus out. It's just written differently. Sorry, this is not my image, but this is in versus out. So we have what's leaving versus what's coming in, similar as the radium situation. We have decay, which is a combination, we have the loss to the atmosphere, which is a combination of decay, and in the case of radon, because it's a gas, wind. You have to take wind into account, because the more wind you have, the more radon will be lost. And then we have what's coming in. So what could be coming in via rivers, what could be coming in via diffusion and desorption, and what's left over is our SGD. That's our SGD. So how do we calculate groundwater flux from radon in a bay? So the first calculation is quite simple, and this is the minimum quantification. So this is not including atmospheric evasion. This is not including from wind, not including atmospheric evasion from wind. It's the radon excess in the water, times what's being removed via the flux out over the radon in the groundwater. So what's the radon excess in the water? The radon excess is what you calculated or what you measured from radon in the bay minus 226 radium, which is also being measured in your radon detector, and so you can just use the program to remove the radium 226 from the value of radon in the calculation that you see on your screen. So this is the minimum groundwater is the radon excess times what's leaving through the inlet over the radon in the groundwater. So this is essentially like your tidal prism from the first radium discussion. That's your minimum radon or your minimum groundwater. But if we really want to evolve our understanding or evolve our understanding of radon, we need to take into account some other things. So this is your, once again, your maximum groundwater discharge. Now we're taking into account your radon excess plus the loss to the atmosphere plus the loss to decay times the amount that's going through the inlet over your groundwater and member. So how do you calculate these things? So J Atman, how much is being lost to the atmosphere via wind, is based on this equation. I think it's a little complicated. Where W is wind speed, H is the effective depth of radon mixing, which in shallow water is basically the depth of the water. Sorry, W is not wind speed. W is the estimated current of the water. U is wind speed. So here, with this information, we can understand how much is being lost to the atmosphere. So you need your estimated current. You need your average depth of the water. You need your wind speed. You need your residence time of the water in your bay. And you need to know the effective depth, which is essentially the same as your depth in a shallow water system. And with this, it looks a little bit complicated, but it's really just a plugging in numbers issue. You just have to plug the numbers in. So if you know your current, then you just plug that in here. If you know your depth of the water, you plug that in here and here. Your wind speed you can measure or get from the weather system nearby, and that gets plugged in here. Radon water is different than radon excess. So this is the radon that you're measuring without removing the 226 RA. This is the decay constant, and that's the residence time of your bed. So with this information, you can quantify SGD. What's often not calculated is the production from suspended sediments, which is that desorption experiment that we talked about last time. If you're working in an open water coast, the accepted idea is that your radon is really zero outside of about a 1 kilometer distance from your shore. So your box ends at that 1 kilometer level. The question that I don't fully understand, and it's something that needs to be probably explored more in the future, is what is the exchange out from that box? That's why there's still a lot of uncertainty in the radon measurement. In bays, it's easier because you can just measure that in an inlet. But in an open water coast, how do you know what's the exchange between your box, in and out of your box? So how much water is moving offshore versus onshore? That's difficult. That's difficult. And that's something that, if you're interested in this topic, is worthwhile exploring. How do you determine your box? What's going in and out of your box? Your radon in your groundwater is the same story as your radon in your groundwater for radium, except you don't have to take into account the processes that are occurring in the subterranean estuary, which means you can collect radon from wells close to the coastline. You don't have to do the pore water measurement directly on the sea. You can, but you don't have to. Wells are better in terms of radon. Okay, we're gonna look at this again a little bit later. We're gonna actually do this calculation once. Okay. All right, so we're about halfway through this. We'll take a 1 minute mental break. While we're taking this mental break, we're going to now switch and say, okay, so radium is problematic, we know this. Radon is better, but probably also a bit difficult to do in open coastal systems to get the exact numbers. It's more of a mapping situation in the open coastal systems where you can see high and low radon to say, this is an area where groundwater is coming out, and this is an area where it's not. It's harder to do a true quantification. We'll try with uncertainties. Why we're taking a mental break is we're going to start with a new story where it's not just radon. All of this stuff led me to the idea of trying to figure out a different way to make this work. To reduce that uncertainty by using something else. And that's going to bring us to GIS. Okay. Good? We'll go. All right. So, I started thinking about this while I was working in Germany on the Baltic Sea. And the Baltic Sea is a fairly large, I wouldn't call it a true sea. It's more like a very large lake, brackish water lake. And because it does have one entrance to the North Sea, but it's very low salinities. The average salinity in the Baltic Sea is about 10 parts per thousand. So it's very low salinity. And what we have in the Baltic Sea is we have a massive eutrophication issue along the coastline of Germany and Poland. And so we know that there's a lot of nutrients getting into the Baltic Sea. The other thing that we know is that there's a bit of elevation going down into the Baltic Sea with quite high conductivity, high hydraulic conductivity soils nearby. So there should be a lot of nutrients getting into the Baltic Sea via SGD. So here's your Baltic Sea. Once again, there's just kind of like this one little inlet into the Baltic Sea, and you have very low salinities in most of the Baltic Sea. The other thing with the Baltic Sea, and I love old maps, is that the Baltic Sea is a very peaceful place. You know, here in the North Sea, we have lots of sea monsters. Because it's very dangerous in the North Sea and the Baltic Sea. You know, it's pretty chill out here. These guys are just hanging out. These guys are going skating on the Baltic Sea. You know, that guy's horseback riding. So it's a really peaceful place. And but it's also a place where we know that there must be groundwater coming down. So we're talking about really this area of the Baltic Sea down here, which is our study. The SGD that we find in the Baltic Sea is not going to be spring-based SGD because it's really just these loosely consolidated sediments along the entire coast. It's not fractured rock or limestone or volcanic areas, so it's most likely land-derived, so not this recirculated seawater, hopefully, because there's also very low tides in the Baltic Sea. It's only 10 centimeters, so there's not really that much recirculation. And located close to shore. So we tried to do some radium mapping along the Baltic Sea from basically the Danish border all the way to almost the Polish border. And we found fairly low counts of radium. It wasn't very telling. And honestly, it was just kind of not, it was giving us strange numbers with the radium. Radon mapping, we wanted to go as close to shore as possible, but it was a bit difficult. So we started to think about, is there a different way for us to find the SGD? And we started to think about hydrogeological modeling, which is probably close to some of your hearts. And we were thinking about fluid potential. How does groundwater flow? So groundwater essentially flows via fluid potential lines, so which equals the gravitational attraction of the Earth and the hydraulic head. And since gravity is constant, we don't really have to worry about it. So basically the fluid potential equals the hydraulic head. Fluid potential equals the hydraulic head. So what's the hydraulic head? The hydraulic head is the sum of two components, the elevation head and the pressure head. But as I said, in the coast of the Baltic Sea, we're talking about loosely consolidated sediments, an unconfined aquifer. So essentially, the pressure head is the water table, and at the water table, the pressure head is 0 because it's in static equilibrium. So what that means is that the hydraulic head is essentially just the elevation head. And what that means is that fluid potential equals elevation. So water, even if it's underground, will flow downhill. It will flow from high elevation to low elevation. So the groundwater flow direction is controlled by elevation. So maybe the solution is that the fresh groundwater will flow perpendicular to these equal potential lines. We know this. This is clear in hydrogeology. But that these equal potential lines are due to the elevation head, and the elevation head tends to be due to surface elevation differences. So the higher the surface elevation, the higher the elevation head is. So it's almost like, even though it's underground, groundwater will flow downhill. Groundwater will flow downhill. So with this knowledge, I started to think about, well, we know that there are some uncertainties in radar measurements. Maybe we can improve this with simple elevation models. So can we just use digital elevation models to determine where groundwater is going to come out? Now, of course, this is not going to work everywhere. It's not going to work where you have confined aquifers. It's not going to work where you have lava tubes. It's not going to work in fractured rock aquifers. But maybe in unconsolidated, unconfined aquifers, this is a great way of trying to find groundwater. And maybe we can even predict the amount of groundwater based on the GIS. So we get there. So once again, the idea is use the GIS to find these equipotential lines based on digital elevation models, and if we have it, hydrogeological maps. So we did this in Germany. We started this in Germany. We went to the area where we live, which is here in Kiel, Germany, and we got a very low resolution digital elevation model. And we simply tried to find out where groundwater should flow based on elevation. So if you have ArcGIS, QGIS used to do this, QGIS now has a much simpler way, but if you have ArcGIS, you can essentially take an elevation raster, which is a pixelated image of the world, right? A digital elevation model is just pixels, and each of those pixels have one value, and that value is elevation. As pixels, and you can run what you call flow direction. So flow direction says, if I'm in this pixel, I'm going to flow to the pixel with the lowest elevation near me. You're always going to flow downhill fastest. Right? So you're not going to flow uphill from 55 to 58 or from 55 to 61. You might flow in this direction, you might flow in that direction, but you're going to flow in this direction because that's the biggest downhill difference. So you get a flow direction. And ArcGIS calculates those flow direction and gives it values of 1 if you're flowing to the, what is that, the west, 2 to the southwest, 4 to the south, 8 to the southeast, 16 to the east, 32 to the northeast, 64 to the north, and 128 to the northwest. It just gives it that value. And then you get a raster that looks like this. And you get a raster that looks like this. So it gives you a random flow direction raster. And this is what my flow direction raster looks like. It's a bunch of mumbo jumbo, but that is what it is. It just tells you where each pixel is flowing. And then you can calculate, use this flow direction to calculate a flow accumulation. And your flow accumulation is essentially how many pixels flow into my pixel. How many pixels flow into my pixel? So for example, here, all these zeros mean no pixels are flowing into this pixel, if it has 0. 1 means 1 pixel flows into that pixel. 2 means that 2, and so on and so forth. And you can begin to see, by flow accumulation, kind of the way your river or your groundwater might move. And then you can create a flow accumulation map. You can create a flow accumulation. So here in the darker colors, we have large flow accumulations. And we know actually that some of these are rivers. We know that some of these are rivers. So if we look at, for example, these 2 points here, we say, okay, this is a high flow accumulation, and that's another flow accumulation is a bit lower, and the one that's red, if we look in really close, is a river that comes out. And if it's a river, we can kind of forget about it. It's no longer submarine groundwater discharge. It's a river. But what if there's flow accumulation and there's no river? What if there's flow accumulation and there's no river? So for example, in these points, A, B, C, there were flow accumulation but no river. So we went to them and we went A and we said, oh no, look, there is something there. That's a river. Or some sort of, there's probably some sort of conduit under here. That's not submarine groundwater discharge. But then we went to B, and we just look at the satellite image and we say, oh, maybe there's something, but we don't really see a river here. And C, same deal. We saw something, but we don't see a river. So we actually went to those spots, and when we went to those spots, we saw that there was groundwater in the area. We were actually measuring it and finding that this was low or no salinity water right on the beach. So maybe you can use this flow accumulation to understand where groundwater might be coming out. It's very quick. It's a very quick thing to do. We'll do it later. And you can then take your coastline and say, hey, these are potential spots where we have high flow accumulation close to the coast. Maybe these are spots where groundwater is coming out. And you could go, especially if you have a student, you could go and send them to all of those spots and look if there's groundwater coming out, or if there are rivers. And you get a quick and dirty image of your coast. And then you could go in and you see, you actually maybe measure SGD in some of these places. So I got blue here, I got SGD here, I got blue here, I got SGD here. I'm starting to see this works. And if you're lucky, you have hydrogeological maps. And with your hydrogeological maps, you can then improve your model of where the SGD might be coming out and get an index of areas of high potential SGD and low potential SGD. And then you can go out and look for them. And when we did, we really found in the areas of high potential SGD, we found a lot of intertidal SGD that we saw. Not rivers, but really these pulses that were coming out. And this is fresh water that's coming out here. And then we went to the area and we actually did a bunch of cores in the area or piezometer samples in the area, and we measured the salinity in the surface water and the salinity in different depths, and we tried to see where we have high SGD potential, we actually had quite low salinity at depth. So the surface water is the surface water, that's just open water, but there was no salinity at depth where we expected to see high SGD. So there's fresh water coming out in those spots. So we can take a DEM, and we can get a sense of where fresh water is coming out very quickly. We can get a sense of it. And if it's a river, then we just cross it off. This is not groundwater discharge, and we try to focus on the spots where it is potentially groundwater discharge. So we did this in a couple of different spots, and this is where radon comes back in. We wanted to use radon to kind of validate this idea. So the first place we did this was in Port Jefferson Harbor, New York. Port Jefferson Harbor, New York is essentially a sandy, unconfined aquifer with a bit of elevation near it. And we went there and we did a radon map along the coast of Port Jefferson Harbor. And that was our track log. And then we changed these into individual segments so we could understand each of these individual segments. And we, there you can see those individual segments. And then we added the radon values to those segments. And you can see high radon is in the warmer colors and low radon is in the colder colors. So we get our radon activity, and this is the way we traveled around the bay. This is the way we traveled around the bay. And this was kind of the radon activity that we saw. Really high radon activity in this area here. Lower radon activity around here. Low radon activity around here. And high radon activity in this area here. So then we added our digital elevation model to the area. You can see we're not talking a lot of elevation, up to 86 meters at the highest point. And we ran our flow direction, we ran our flow accumulation, and we see we have high radon in the area of high accumulation here. So once again, this is a good sign that this digital elevation model study is a good way of quickly finding our locations of SGD. You might say, why didn't we measure here? This is a port area, we couldn't go in here, this whole area is blocked off. But there is a river coming out here, so it's probably not the case. So we wanted to do it again, and we're gonna do this together in a few minutes. We wanted to do it again in another location nearby, the Niantic River in Connecticut. Once again, this is a sandy, unconfined surface aquifer, but in this case, it's actually lying above granite, so it should have higher radon values than the Long Island one. And it's a very closed system. There's only one small inlet, so it's a good system to test this idea in. So we went to the Niantic and we measured radon not just along the coast, but kind of all over the Niantic River. And then we ran the flow accumulation for the Niantic River. And we see there's lots of little flow accumulation around the area, but a lot of it's coming in here, in this area up here. So if you look up here, we have a lot of flow accumulation that's coming into this area, and we have high radon in that area. We have high radon in that area. So we're really beginning to see that this methodology of just doing a digital elevation model might be a really nice way to understand where groundwater is coming out. This little spot here, this is a surface stream, but all of these were nothing. We couldn't find anything when we went there. So these were all kind of just points of discharge, but not surface discharge. So, coming back to our calculations, how can we now use GIS and a DEM to actually calculate SGD? Well, it's quite simple. Basically, you can use, for the area, your recharge. So your recharge is your precipitation minus evapotranspiration minus runoff. Those things you can probably find in most areas. Runoff you can base on the USGS soil runoff curves if you want. To get your recharge per pixel. To get your recharge per pixel. You assume that for an area like this that the precipitation is similar and the evapotranspiration is similar per pixel. You get your recharge per pixel. Then you multiply it by the amount of pixels that you have. And then you multiply it by what we call flow accumulation. Sorry, you multiply it by the area of the pixel. So recharge per pixel, you multiply it by the area of the pixel, so the resolution of the DEM, and then you multiply it by your flow accumulation. So the amount of pixels that made it to the coast in that spot. You remove the rivers, because those river ones are not groundwater, and you can calculate then a discharge. And we did this for the Niantic River in Connecticut, and we got a discharge of 1.2 cubic meters per second. 1.2 cubic meters per second. But as I said, we also did radon there. We also did radon there. So we did a radon calculation. We did the minimum. The minimum was the radon excess. The radon excess, if you remember, was the radon in the water minus this 226 radium that's calculated in the system, times the discharge out of the inlet, over the radon in the groundwater that we measured in wells nearby. And we got an SGD, the minimum, of 0.73 cubic meters per second. A little bit better than our radium stuff. And then we did the maximum radon calculation. We did the maximum radon calculation. So this we take into account the atmospheric evasion and the decay as well. We got the wind speed, we got the average depth of the water, we got the current of the water, and in this case, we measured an SGD, oh, where is it? Of 5.5 cubic meters per second. So this number falls really well in between these numbers. So these are a really nice sign that A, radon seems to work pretty well, and the digital elevation model method seems to work pretty well. If you take what you are able to calculate, what's possible, what in that area, what could the potential highest amount of discharge be in that area just by the watershed multiplied by the recharge, it was only 4 cubic meters per second. So really right on these lines, right on these lines. What's nice about this is inherently just fresh water. Whereas radium always measures seawater recirculation, this is just fresh water. So if you can then measure the nutrients in the wells, then you can really get a flux of nutrients. You get a flux of chemicals into your coastal zone. Because we know that this is fresh water. But it also suggests that radon is essentially measuring fresh water, or at least a lot closer to it than the radio. So it's a good way of doing it. And I want to show you briefly how to do this, because I think it's a really nice exercise. Do you guys want to see how to do this? Does anybody know how to do this in ARC yet? You do. Okay. Does anybody use QGIS? Okay. All right, so I'll show you, because QGIS just made this really simple.
How different is in GIS?
Sorry?
How different is in ArcGIS?
It's just you have to do the flow direction and the flow accumulation steps. So what I said earlier in ArcGIS, and to be honest, I haven't used Arc in a couple of years, so maybe they've improved it. But you have to measure first. There's tools: flow direction, flow accumulation. Yep. So, but QGIS has made this really simple with a plugin. So I'm going to show you briefly how to do this. If any of you have the data, feel free to join me.
Si alguno le falta el DEM, si quieren hacerlo, ahí me pasó el DEM que tiene que usar de ejemplo en el pendrive. La listita estaba por ahí dando vuelta, dame esa, ¿se anotó?
Sean, a question. Coming back to the radium and radon examples, did you perform the same work or the radium measurement and the radon measurement in the same place? Let's say the Beach Lagoon and the other place?
So,
the results?
I've never done both myself. But there's a few people who have. There's a few publications looking at radium and radon comparisons, and they're never perfect. You know, there's the radium is always measuring higher values.
Higher values.
Yeah.
So those values are saying coming from radium measurements that you have 4, 5, or even 10 times the SGD water against the river inflows.
Yeah.
It's really wrong right now.
Yeah, so a lot of publications are out there about radium, and you'll see that every single one of them says recirculated seawater or subterranean estuary. So they're all saying that it's very, yeah, absolutely, yeah. But there's several comparisons out there between radon and radium. Okay, so we're going to start with a very simple digital elevation model. And I don't know what your access is to digital elevation models in Argentina are. But for example, in the United States, digital elevation models are really easy to find online and free. So we're going to use one. It's a digital elevation model that I've already kind of cut a bit to make this easier. And it's a quite low resolution digital elevation model. The higher the resolution you have, the better. That being said, to get digital elevation models these days, at low resolution are pretty much available anywhere. You can use the Landsat data. At high resolution, honestly, a drone these days is cheaper than a radon detector. So it's probably something to think about. If you have a drone, you can do it quite easily, fly over a coast at high resolution. So I'm going to add this data set, this raster data set, Niantic, and this is what it looks like. So it's just a simple digital elevation model. The higher values are white, the lower values are black. And just so you see, if I add a background map to this, you can see that it's in the kind of the right area. You'll see in a minute, but it's cut here. That's the Niantic River, which I just showed you. And this CRS, I'm going to make sure is in the Connecticut coordinate reference system. So it's down here. 6434. 6434 is the Connecticut coordinate reference system. So once again, we have the Niantic raster. It goes from 0 to 273 feet. The calculations are in feet. It's 6434. Don't ask me why Americans still use feet, but we do. But I've been living in Europe long enough to know meters. Okay, so we start with a digital elevation model. Quite simple digital elevation model. And I always think it helps your mind to make this look good. So I would change the symbology of this digital elevation model to something that's clearer to understand. So I would add, right click on the file, go to properties. It's going to ask you about this transformation, just hit OK. Go to symbology, and you change it from the single band gray to a single band pseudo color. And then there are some beautiful color ramps in QGIS for digital elevation. So if you go to the drop down next to the color ramp, by the way, if anybody wants to stop me, feel free. And I go to create new color ramp down here. And I choose CPT city, catalog, CPT city, hit OK. And a bunch of color ramps come up. And I scroll down till I get to these DEM, digital elevation model print color ramps. And there's a lot of them, just click on one of them. And then you want your 0 elevation to be blue because it's the sea. So 0 is blue. And then you can put your land at, I don't know, 0.1. So just above the sea. And now you get kind of a nice colored digital elevation model. And if you want to make this look really pretty, which I also like to do, is there's a great tool, raster, analysis, hill shade, and you use your Niantic layer, give it a Z factor of 4, so how much you want to exaggerate the vertical. You can run that. You get a hill shade. You put your Niantic on top of the hill shade, and you make your Niantic in properties, transparency, like 50% transparent. Hit apply, okay. And you now have like a really nice looking digital elevation model. I like that, it helps my mind work. And it's amazing how easy it is to make these otherwise, if for fresh water, otherwise your aquifer will be changing its volume. And maybe it's changing its volume because people are pumping or whatever, but in the absence of people, theoretically, over time, that aquifer should be quite stable. So what's going in is what's going out. And we can do this via GIS pretty quickly and pretty easily. So I think maybe let's simplify things instead of making it too complicated, at least to start, at least as a first approximation. Okay, we have a few minutes left for questions, I think. Yeah?
Hi. Sorry, the base data used to the Cushi's map, you said that it was a digital elevation. What does it? Not that much.
It was a digital elevation model, which essentially is just a pixelated image of an area, and each pixel has one value in it, and that value is elevation. And you can make those via satellites, you can make it via aerial images or drones these days. And one of the important points is the resolution, so how large is a pixel? And now you're getting sub-meter resolution with drones, but you can also get free online 30 meter resolution for larger areas. And in many parts of the world, like the United States, you can get essentially meter resolution also free online. Just remember that the higher the resolution that you have, the more intensive computing it is. And so if you're using a large area and you have a very high resolution, that laptop will start smoking and maybe blow up. So you have to think about what you can actually do, what you can process. So when we're back again, when we're back again in 2 weeks, or I'm sorry, 1 week, we will be moving towards, let's say, some more practical applications of coastal protection in terms of nature-based solutions. There will be some connection with groundwater, and then the final seminar will be on water resources in small island developing states, but really focusing on groundwater, but in this case more groundwater, seawater interactions where seawater is coming into land. Then we'll go from there. I can send Silvina some references, and then you can maybe pass it on to this group in the next weeks.
Yeah, sure.
Something like that. Sounds good. Thank you.
Thank you.